There's a place beneath the Swiss-French border where we've built one of humanity's most audacious machines. It's a tunnel 27 kilometers in circumference, buried 100 meters underground, containing a particle accelerator so powerful that when it runs, it recreates conditions that existed for just a fraction of a second after the Big Bang. This is CERN, the European Organization for Nuclear Research. And what happens inside this machine is reshaping our understanding of reality itself. For most of human history, we've asked the same fundamental questions. What is the universe made of? What are the basic building blocks of existence? How do forces work? What is matter? We've progressed from philosophical speculation to empirical science. We've learned that matter is made of atoms. Atoms are made of electrons, protons, and neutrons. Protons and neutrons are made of quarks. But the deeper we dig, the more we realize we don't understand. What are quarks made of? Do they have a substructure? What are the forces that hold the universe together? Why does matter have mass? Why does the universe exist at all? CERN was built to answer these questions. By smashing particles together at nearly the speed of light, we can probe the fundamental nature of reality. And what we've discovered there has fundamentally changed our understanding of physics. Let me start with the history. CERN wasn't always at its current location. The organization was founded in 1954 by 12 European nations who recognized that to do world-class physics research, they needed to pool resources across borders. The Cold War was in full swing. The Soviet Union and the United States were competing for scientific supremacy. Europe decided it couldn't compete with either superpower alone, so they united. CERN is perhaps the greatest achievement of international cooperation in modern science. It predates the European Union by decades. It's a living example of what nations can accomplish when they work together. The early years were focused on using accelerators to create new particles. In the 1960s and 70s, CERN built increasingly powerful machines, each discovering new particles and deeper insights into the structure of matter. But the real ambition came later. In 1984, CERN approved the construction of the Large Electron Positron Collider, or LEP. This machine was revolutionary. It would collide electrons and their antimatter counterparts, positrons, at high energies. LEP operated from 1989 to 2000 and made tremendous contributions to particle physics. It precisely measured properties of the Z and W bosons, particles responsible for the weak nuclear force. But LEP had limitations. The energy it could achieve was constrained by a fundamental physics limitation. When you accelerate electrons to very high speeds in a circular path, they radiate energy away. This radiation, called synchrotron radiation, limits how energetic you can make the electrons. To go higher in energy, you needed to use particles that radiate less. Protons are nearly 2,000 times heavier than electrons, so they radiate much less energy for the same acceleration. This is why the next machine was the Large Hadron Collider, the LHC. The LHC is the most powerful particle accelerator ever built. It's designed to collide protons at energies of 14 TeV. That's 14 trillion electron volts. To put this in perspective, that's roughly 1,000,000 times the energy of a single proton moving at the speed of light in a laboratory reference frame. At these energies, something remarkable happens. The temperatures created in the collision are so high, hotter than the core of the sun by a factor of 1,000,000, that the normal rules of physics break down. Particles that don't normally exist at low energies can be created. Forces that appear separate at low energies can merge into unified forces. The fundamental structure of reality reveals itself. The LHC was a massive undertaking. Construction began in 1998. The tunnel was repurposed from the old LEP accelerator, which saved enormous costs. Inside the tunnel, powerful magnets create a circular track for protons to travel. The superconducting magnets have to be cooled to 1.9 Kelvin, colder than the temperature of outer space. To achieve this, the LHC uses liquid helium in vast quantities. Around the tunnel are 7 main experimental detectors. The 2 largest are ATLAS and CMS. These are massive detectors, several stories tall, containing millions of sensors designed to record what happens when protons collide. When a proton collides with another proton traveling in the opposite direction at nearly the speed of light, the collision releases enormous energy in a tiny volume. This energy is converted into new particles, which are created for an instant before decaying into other particles. The detectors have to record the properties of these particles, their energy, momentum, charge, and type within nanoseconds. The first beam circulated in the LHC in 2008. Scientists were ecstatic. After a decade of construction, the machine was finally running. Then, 9 days later, disaster struck. A magnet quenched, lost its superconducting properties. The enormous energy stored in the magnet was released violently, melting parts of the accelerator and damaging the tunnel. It took over a year to repair the damage. Scientists and engineers had to redesign parts of the machine, improve safety systems, and gradually bring the LHC back online. When it finally restarted in 2009, it operated at lower energy than designed, but it was working. And over the next few years, the LHC gradually increased in power. By 2012, the LHC was operating at close to its design energy. And on July 4th, 2012, CERN announced a discovery that would reshape particle physics. They had found the Higgs boson. To understand why this was so important, I need to explain what the Higgs boson is and why physicists had been searching for it for nearly 50 years. In the 1960s, physicists developed the Standard Model of particle physics. This model describes all the known particles and the forces between them. The Standard Model includes quarks, which make up protons and neutrons. It includes leptons, like electrons. It includes photons, the particles of light. It includes gluons, which hold quarks together. It includes W and Z bosons, which mediate the weak nuclear force. But the Standard Model had a problem. The equations that describe these particles predicted that they should all be massless. Photons are indeed massless, but electrons have mass. Quarks have mass. W and Z bosons have mass. Why? The theory didn't explain it. In 1964, physicist Peter Higgs and others proposed a solution. They suggested that the universe is permeated by a field, the Higgs field. As particles move through this field, they interact with it, and this interaction gives them mass. Particles that interact strongly with the Higgs field are heavy. Particles that interact weakly are light. Photons don't interact with the Higgs field at all, so they remain massless. But this Higgs field had a prediction. It should have excitations, like any field, and these excitations would be particles, the Higgs boson. For 50 years, a physicist searched for the Higgs boson. They looked in smaller accelerators. They looked in higher energy collisions. They calculated its properties and narrowed down where to look. But it eluded them. The Higgs boson is massive, about 125 times heavier than a proton. To create it, you need enormous energy. The LHC was powerful enough. The July 4th, 2012 announcement confirmed that CERN had found it. The Higgs boson existed. It had the properties predicted by the theory. This was one of the greatest moments in science. It wasn't just the discovery of a new particle, it was experimental confirmation of a major theoretical prediction. It validated the Standard Model. But it also left many questions unanswered. The discovery of the Higgs wasn't the only way CERN has transformed our understanding. Let me talk about other discoveries and research areas. One major area is the study of fundamental forces. We know there are four forces in nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity holds planets in orbit and keeps us on the ground. Electromagnetism controls chemistry and light. The strong force holds nuclei together. The weak force is responsible for radioactive decay. These four forces have very different strengths and characteristics. Gravity is extremely weak compared to the others. Electromagnetism and the weak force seem unrelated, but physicists have shown that these apparent differences are superficial. At high energies, the electromagnetic force and the weak force merge into a single unified force called the electroweak force. Experiments at CERN have measured this unification precisely. They've shown that as you increase the energy, the two forces come together just as theory predicts. This is profound. It suggests that at even higher energies, the other forces might also unify. Perhaps gravity unifies with the other forces. Perhaps all forces merge into a single unified force. This is the dream of physicists, a theory of everything that describes all forces and particles in a single mathematical framework. We're not there yet, but CERN is helping us move in that direction. Another major discovery involves antimatter. For every particle of matter, there's an antimatter counterpart. The electron has the positron. The quark has the antiquark. When matter and antimatter meet, they annihilate each other, converting entirely to energy. This is profound because it raises a question. The Big Bang should have created equal amounts of matter and antimatter. They should have annihilated each other. Nothing should have been left. But we exist. The universe is made of matter, not antimatter. Why? There must be a slight asymmetry in how matter and antimatter behave. Physicists call this CP violation. CERN has measured CP violation in several particle systems and found that the observed asymmetry is exactly as predicted by theory. But the asymmetry is too small to explain why the universe is made of matter. There's a deeper asymmetry we haven't found yet. This is an area of active research at CERN. Finding the source of matter-antimatter asymmetry could revolutionize our understanding of the early universe. Let me talk about another major research area: the top quark. There are 6 types of quarks: up, down, strange, charm, bottom, and top. The top quark is the heaviest, weighing as much as a gold atom. It's so heavy that it decays almost immediately. It's never observed in isolation. It immediately transforms into lighter particles. But by studying the properties of top quarks and their decay products, physicists learn about the weak force and the structure of the Standard Model. CERN has produced millions of top quarks and precisely measured their properties. This data helps us understand the fundamental nature of quarks and forces. Another area of major interest is exotic particles and new physics beyond the Standard Model. The Standard Model, despite its successes, is incomplete. It doesn't include gravity. It doesn't explain dark matter, which makes up 80% of the matter in the universe. It doesn't explain dark energy, which is accelerating the expansion of the universe. There must be new physics beyond the Standard Model. Physicists have proposed many candidates for new particles and forces: supersymmetric particles, which have one spin unit different from standard model particles; technicolor particles, which could explain the Higgs without actually needing a Higgs field; extra dimensions, where particles could move in ways we can't directly see; dark photons, which could mediate forces in the dark matter sector; primordial black holes, which could have been created in the early universe. CERN searches for all of these. We collide protons, record the debris, and look for signatures of new particles or unexpected patterns. So far, we haven't found anything definitely beyond the standard model, but the search continues. This is frustrating to many physicists. We were optimistic that the LHC would discover new particles right away. But the standard model keeps resisting being overturned. Some interpret this as meaning new physics is at even higher energies than the LHC can reach. Others think we're missing something and need new experimental approaches. It's also possible that the standard model is more fundamental than we realized, and extending it requires a truly revolutionary insight. Now let me talk about what happens inside the detectors when particles collide. When two protons collide at the LHC, the collision happens at a single point. From this point, a shower of particles flies outward in all directions. The detectors have to capture information about all these particles. The innermost layer of a detector is the tracking system. It consists of silicon microstrips and pixels that record the paths of charged particles. By seeing how these paths curve in the magnetic field, physicists can determine the particle's charge and momentum. Outside the tracker is the calorimeter. When charged particles hit the calorimeter, they interact with the material and deposit their energy, creating showers of particles. Different particles interact differently. Electrons and photons create electromagnetic showers. Hadrons create hadronic showers with different characteristics. By measuring the pattern and energy of these showers, physicists can determine what type of particle created them. Outside the calorimeter is the muon chamber. Muons are heavier cousins of electrons. They're so penetrating that they pass through the calorimeter nearly unscathed. The muon chamber records their tracks and determines their properties. All of this data is recorded digitally. A modern detector at the LHC produces about a petabyte of data per second, but a petabyte per second is too much to store. Physicists use triggers, special algorithms that run in real time on the detector data and decide which events are worth keeping. Most collisions at the LHC are uninteresting. They produce the same kinds of particles we've seen a billion times before. But occasionally, a collision is unusual. Perhaps it produces an unexpected pattern of particles. Perhaps it has unusually high energy. These rare events might indicate new physics. The trigger algorithm has to recognize them and tell the detector to save the data. Currently, the LHC produces about 40 million collisions per second. The trigger system filters these down to about 1,000 events per second that are saved to disk. Even at this rate, CERN saves about 100 terabytes of data per day. This data is sent to computing centers around the world. Thousands of physicists analyze it, looking for patterns, testing hypotheses, searching for new particles. This is how modern particle physics works. It's a collaboration between experimentalists who build and run the detectors and theorists who predict what to look for and interpret what we find. Now let me talk about the physics of particle collisions in more detail. When two protons collide at the LHC, they're not colliding as hard, solid objects. Protons are composite objects made of quarks and gluons held together by the strong force. In a high-energy collision, the protons don't collide head-on. Instead, it's a quark or gluon from one proton colliding with a quark or gluon from the other proton. The collision creates enormous energy in a tiny volume. This energy is converted into new particles which fly outward. But here's the thing. These new particles immediately interact with the strong force and create showers of more particles, all moving outward. We observe jets, collimated streams of particles flying in a particular direction. By reconstructing the jets, we can infer what happened in the initial collision. If we see two jets of particles with high energy and no leptons, it suggests a collision between two quarks or gluons. If we see a jet and a high-energy electron, it suggests a collision involving the weak force and the creation of a W boson. If we see a jet, a high-energy muon, and a large amount of missing energy, it might suggest the creation of a heavy particle that decayed invisibly. By studying these patterns, physicists reconstruct the events that occurred at the subatomic scale. This is possible because physicists understand the fundamental interactions and can calculate the probabilities of different outcomes. The calculations involve quantum mechanics and special relativity. We have to account for all the different ways particles can interact, all the quantum fluctuations, all the possible intermediate states. These calculations are enormously complex. A single collision can involve thousands of different quantum processes happening simultaneously. But fortunately, we have computers. Physicists use Monte Carlo simulations, where computers generate billions of simulated collision events according to the laws of physics. Then we compare what the simulation predicts with what we actually observe. If they match, our understanding of physics is correct. If they differ, we found an anomaly that might indicate new physics. Now let me discuss the significance of some specific discoveries. The Higgs boson discovery, as I mentioned, confirmed the Higgs mechanism for mass generation, but more importantly, it proved that the LHC works. Before the Higgs discovery, there was skepticism. Would the LHC really be able to discover new particles? Would the background noise from ordinary collisions drown out the rare signal? The Higgs discovery proved the answer was yes. We could find a rare particle among billions of background events. The detector and analysis techniques worked. This boosted confidence that the LHC could find other new particles if they exist. Another important discovery is the precise measurement of the W boson mass. The W boson mediates the weak force. Its mass was measured at previous accelerators, but with limited precision. CERN has improved this measurement dramatically. The precision is now better than 1 part in 1,000. Remarkably, when you use precision measurements of W and Z boson properties to calculate predictions for other standard model parameters, there's a discrepancy. The measurements suggest the Higgs mass should be different than what was observed, and there are other tensions between different precision measurements. These tensions might indicate new physics. The discrepancies are small, but they're consistent across multiple independent measurements. This is exciting because it suggests something beyond the standard model is affecting these measurements. Another area of great interest is flavor physics, the study of how different types of quarks decay. B mesons are particles containing a bottom quark. When they decay, they can produce interesting decay modes that might involve new particles. CERN has observed rare B meson decays and compared them with standard model predictions. Again, there are small discrepancies that might indicate new physics. Individually, each discrepancy is not significant, but together they paint a picture of something we don't yet understand. This is how particle physics discovery works in the modern era. We don't expect to find a smoking gun. a clear, unambiguous new particle. Instead, we look for small deviations from predictions that accumulate evidence for new physics. Now let me discuss the challenges CERN faces and where the field is heading. One major challenge is luminosity. Luminosity is a measure of how many collisions per unit time the accelerator produces. The LHC currently produces about 40 million collisions per second, but many particles physicists want to study are produced extremely rarely. To find rare events, you need more collisions. This requires higher luminosity. CERN is planning an upgrade called the High Luminosity LHC, or HLLHC. This will increase the luminosity by a factor of 10. To achieve this, CERN is installing new magnets, upgrading the detectors, and improving the accelerator systems. The HLLHC will come online in the late 2020s and will continue running into the 2030s. With 10 times more data, physicists hope to find rare processes that might indicate new physics. Another challenge is energy. Some theories of new physics predict particles that are only created at energies higher than the LHC can currently achieve. There are proposals for even larger accelerators. The Future Circular Collider, or FCC, would be 100 kilometers in circumference and could operate at energies much higher than the LHC. But constructing such a machine would cost hundreds of billions of dollars and require international coordination on a massive scale. For now, scientists are focusing on maximizing what we can learn from the LHC and its planned upgrades. Another area of intense activity is theoretical physics. We know the standard model is incomplete, but what comes next? Many physicists are working on candidate theories. String theory proposes that fundamental particles are actually tiny vibrating strings. Different vibrational modes correspond to different particles. Loop quantum gravity proposes that space-time itself is quantized, made of tiny loops. Supersymmetry proposes that every particle has a heavier supersymmetric partner. Technicolor proposes a new strong force that explains the Higgs without needing an elementary Higgs field. Extra dimensions propose that there are spatial dimensions beyond the three we perceive. Each of these theories makes different predictions. Experiments at CERN help us test these predictions and narrow down which theory, if any, is correct. The excitement in particle physics comes from knowing we're at a frontier. We can't yet see beyond the standard model directly, but we can see hints of new physics. The question is, what lies beyond? Now let me discuss CERN's role in society and culture. CERN is far more than just a physics laboratory. It's a symbol of international cooperation, of the pursuit of knowledge for its own sake, and of humanity's deep desire to understand the universe. The organization operates with a unique culture. Scientists from all over the world work together. Nationality, ethnicity, and religion are irrelevant. What matters is the quality of your science. This collaborative culture has been one of CERN's greatest strengths. The best ideas win, regardless of where they come from. CERN has also had cultural impact beyond science. The organization is in the popular imagination. Science fiction writers reference it. Movies and TV shows feature CERN. There's a legitimate reason for this popular interest. The questions CERN addresses are profound. What is matter made of? What forces govern the universe? How did the universe begin? These are questions that have interested humanity for millennia. I should also mention that CERN has been a cradle for technological innovation. The world's first web server was built at CERN in 1989 by Tim Berners-Lee. He needed a way for physicists in different countries to share documents and research findings easily. His invention, the World Wide Web, has transformed human civilization. CERN has also pioneered techniques in computing, data analysis, detector technology, and superconducting magnet technology. Many of these innovations have found applications outside physics. Superconducting magnets are used in MRI machines. Detector technologies have applications in medical imaging. Computing techniques developed at CERN are used in industry. CERN is also a test of whether humanity can cooperate at the highest levels. The Large Hadron Collider involved thousands of physicists and engineers from dozens of countries. People who might ordinarily be rivals or even enemies worked together. Scientists from the United States and Russia collaborated despite geopolitical tensions. Israeli and Palestinian physicists worked on the same experiments. This is remarkable. It suggests that a shared commitment to understanding nature can transcend political and personal differences. Now let me discuss some of the philosophical implications of CERN's work. One major implication concerns the nature of reality. The Standard Model describes nature at the subatomic level, and it works remarkably well. But it raises deep questions. Why these particles? Why these forces? Why these masses? The Standard Model has many parameters, numbers that describe the properties of particles and forces. There's no explanation for why these numbers have the values they do. The electron mass, the quark masses, the coupling constants of the forces. These are just input into the theory. The theory doesn't explain them. This is puzzling. It suggests there's a deeper level of reality we haven't yet accessed. Another philosophical implication concerns the role of mathematics. The laws of physics are described by mathematical equations. The Higgs field is a mathematical field. Quarks are mathematical entities. Does mathematics describe reality, or does reality exist independently of mathematics? This is an ancient question in philosophy, but particle physics makes it concrete. The precision with which mathematical theories describe nature is astonishing. Sometimes experimental results agree with theoretical predictions to 1 part in a billion. How can mathematics be so effective at describing nature? Is there a deep connection between mathematics and reality that we don't yet understand? Yet another philosophical implication concerns determinism and quantum mechanics. At the subatomic level, quantum mechanics reigns. Events are described by probabilities, not certainties. We can predict the probability that a decay will occur, but not when it will occur. We can predict the probability of finding an electron at a particular location, but not exactly where it will be. This seems to contradict our intuition that the universe is fundamentally deterministic. If you know the initial conditions of a system, you should be able to predict its future. But quantum mechanics says that's impossible. There's fundamental randomness built into nature. Yet remarkably, the randomness averages out. When you look at trillions of particles, the quantum randomness cancels out and you get classical behavior. This raises profound questions about the nature of probability, randomness, and causality. Let me also discuss the limits of knowledge. Particle physics is limited by fundamental physics. To study particles, you have to create them with high energy collisions. To create heavier particles, you need more energy. But creating heavier and heavier particles requires exponentially more energy. At some point, the energy becomes so high that gravity becomes important. In fact, theoretical calculations suggest that at energies of about 10 to the power of 16 giga-electron volts, the Planck scale, quantum gravity effects dominate, and our current understanding of physics breaks down. The LHC operates at energies of about 10 TeV, 14 billion times lower than the Planck scale. To probe physics at the Planck scale, we'd need an accelerator with a radius of light years, a physical impossibility. This suggests there are fundamental limits to what we can learn through laboratory experiments about the most fundamental level of reality. We might have to rely on other approaches, analyzing cosmic rays, studying gravitational waves, or using theoretical arguments and mathematical consistency. This is humbling. It suggests that despite all our progress, there might be domains of physics that will forever remain inaccessible to experimental observation. But it also suggests we need new ideas. Perhaps string theory or loop quantum gravity or some completely different approach is needed to understand the deepest levels of reality. Now let me discuss CERN's role in training the next generation of scientists. Thousands of graduate students and postdoctoral researchers work at CERN every year. They come from all over the world and work on the forefront of scientific research. This is where they learn to do science at the highest level. They learn how to design experiments, analyze data, think critically, and communicate complex ideas. Many of these students go on to careers in physics, engineering, computing, and other fields. They carry with them the values and methods they learned at CERN. In this way, CERN serves as a training ground for scientific leadership globally. CERN also hosts lectures, workshops, and summer schools for scientists at all levels. Physicists from around the world come to CERN to learn, collaborate, and share ideas. This creates a vibrant intellectual community focused on pushing the boundaries of our knowledge. Let me discuss some of the experiments currently underway at CERN. ATLAS and CMS are the two main general-purpose detectors. They're looking for a wide variety of new particles and phenomena. LHCb is a specialized detector focused on B-meson physics, studying how particles containing bottom quarks behave. ALICE is designed to study the quark gluon plasma, a state of matter that existed in the early universe where quarks and gluons are not confined into particles but move freely. When heavy lead ions collide at high energy, they create this extreme state for a brief moment. By studying the quark-gluon plasma, physicists hope to understand the conditions in the early universe. There are also smaller experiments, modal searches for magnetic monopoles and other exotic particles. FACER studies long-lived particles that decay far from the collision point. Codex Beta and others look for specific signatures of new physics. Each experiment contributes to a comprehensive search for new physics. Now let me discuss the future of particle physics. In the short term, CERN will complete upgrades to increase luminosity. The HLLHC will collect more data, which might reveal rare processes indicating new physics. In the medium term, proposals for the future circular collider could be developed. This would require a massive international effort and investment, but it would access higher energies and potentially discover new particles. In the long term, physicists dream of even more ambitious projects. An accelerator orbiting the Earth in space? A network of smaller accelerators producing higher energy collisions? A different approach entirely. The future of particle physics depends on whether we can find evidence of new physics at the LHC and whether we can develop new experimental approaches to probe ever higher energies. It also depends on theoretical breakthroughs. A new idea, a new symmetry, a new principle, a new mathematical framework could revolutionize our understanding. This has happened many times in physics history. Einstein's theory of relativity, Planck's quantum theory, Dirac's prediction of antimatter. These came from bold theoretical ideas. not just experimental discoveries. Future breakthroughs might come from similar flashes of insight. Let me also discuss the challenges of doing science in the public eye. CERN's work is publicly funded. Governments provide the money because they believe it's important for society to advance fundamental knowledge. But with public funding comes public accountability. CERN has to justify its work and its budget to taxpayers. This is sometimes difficult. Discovering the Higgs boson was easy to justify to the public, a long-sought particle found. But searching for new physics when you're not sure what you're looking for is harder to explain. Physicists have to communicate why this work matters. They have to convey the excitement of probing the fundamental nature of reality. They also have to address legitimate questions and concerns. Some people worry about the safety of the LHC. Could it create black holes or other dangerous objects? Physicists have carefully analyzed this and concluded that the LHC cannot create dangerous objects. The safety is well established. But communicating this to a skeptical public requires clear, honest communication from scientists. CERN has generally done a good job with public communication. The organization maintains an excellent website, hosts public events, and works with journalists and science communicators. This is important for maintaining public support for fundamental research. Let me discuss one more philosophical implication: the anthropic principle. We've discovered that the universe's properties seem finely tuned for the existence of life. If the electron mass were slightly different, if the strength of the electromagnetic force were slightly different, if any of dozens of fundamental constants were slightly different, stars, planets, and life as we know it could never have formed. Why are these constants so finely tuned? One explanation is the anthropic principle. We can only observe a universe that's compatible with our existence. In a universe with different constants, we wouldn't be here to observe it. Another explanation is the multiverse. Perhaps there are countless universes with different constants, and we just happen to live in one that's life-friendly. Yet another explanation is that there's a deeper theory that explains why the constants must have the values they do. CERN's work contributes to this discussion. By measuring fundamental constants with precision, CERN helps us understand which aspects of physics might be fine-tuned and which might follow from deeper principles. The question of why the universe has the properties it does is not just a question for particle physics. It's a question at the intersection of physics, philosophy, and cosmology. Now let me offer some personal perspective on what CERN represents. CERN represents humanity at its best. It's a place where people from different countries, different cultures, different backgrounds come together to pursue understanding. There's no weapons research at CERN, no profit motive, just a pure desire to understand how nature works. In a world often divided by conflict and competition, CERN is a beacon of cooperation and peaceful collaboration. The facility is open to the public. People can visit, see the detectors, learn about the physics. Walking through CERN, you feel like you're at the center of the scientific universe. The corridors are filled with physicists discussing experiments, sharing data, debating interpretations. The energy is palpable. Everyone is working on problems that matter. This is what science should be. Not isolated specialists working alone, but a community united by curiosity and the pursuit of truth. CERN shows that it's possible to achieve something profound through international cooperation. In an age of nationalism and division, CERN stands as a model for what we can accomplish when we work together. The discoveries made at CERN, the Higgs boson, the precise measurements of particle properties, the constraints on new physics. These will be studied by physicists for generations to come. Future breakthroughs in physics might build on insights discovered at CERN. But even if CERN never made another discovery, it would still be valuable for what it represents: the commitment to understanding, the power of international cooperation, and the human drive to probe the deepest mysteries of nature. Let me address one more important question. What does CERN tell us about the early universe? In the first fraction of a second after the Big Bang, the universe was unimaginably hot. Temperatures were so high that the particles we observe today didn't exist, only a seething plasma of quarks, gluons, and other fundamental particles. As the universe expanded, it cooled. When the temperature dropped below a certain threshold, the quarks couldn't move freely anymore. They combined to form protons and neutrons. This happened about 1/1,000,000th of a second after the Big Bang. Later, protons and neutrons combined to form atomic nuclei. By studying the collision of particles at the LHC, we recreate, in a small volume, the conditions that existed in the early universe. Of course, we can't recreate the exact conditions. We don't have the total energy of the Big Bang, but we can get close. At the LHC's highest energies, we approach the conditions that existed about 1/1,000,000th of a second after the Big Bang. By studying what happens in these collisions, we learn about the early universe. This is remarkable. A machine built in a tunnel under Switzerland allows us to probe the conditions that existed billions of years ago at the moment of creation. This knowledge feeds into cosmology. Cosmologists use what particle physicists learn at accelerators to refine their models of the early universe. Conversely, observations of the universe from telescopes, from cosmic microwave background measurements, from gravitational waves, provide hints about what physics might exist beyond the standard model. Particle physics and cosmology are increasingly intertwined. Understanding the fundamental laws of nature requires both laboratory experiments and astronomical observations. Let me conclude by discussing the profound unknowns that remain. We've made tremendous progress in understanding the universe. We know what atoms are made of. We know the forces that govern particles. We can predict the properties of particles with incredible precision, but fundamental questions remain unanswered. What is dark matter? It makes up 80% of the matter in the universe, but we have no idea what it is. What is dark energy? It's accelerating the expansion of the universe, but we don't understand it. Why is there a matter-antimatter asymmetry? Why do quarks and leptons have the masses they do? Why are there 3 generations of matter? Why not 1 or 4 or 10? Why is gravity so much weaker than the other forces? What happened before the Big Bang? Are there extra dimensions? Is time fundamental or emergent? These questions push the boundaries of human knowledge. The answers, when we find them, will likely reshape our understanding of reality as profoundly as Einstein did, or Planck, or Dirac. CERN is at the forefront of this quest. It's not guaranteed that CERN will find the answers. The true nature of reality might require approaches we haven't yet conceived, but CERN represents humanity's determination to understand. It's a monument to curiosity, to the drive to probe the deepest mysteries of existence. And that's why CERN matters. Not because it will definitely make the next breakthrough, but because it represents what's possible when humanity dedicates itself to understanding the universe. Let me provide much deeper detail on the history and evolution of particle physics that led to CERN. In the late 1800s, scientists discovered the electron. This was revolutionary. It showed that atoms weren't indivisible, as the name suggested, but had internal structure. Then radioactivity was discovered. Atoms could spontaneously transform, emitting particles. In 1911, Ernest Rutherford discovered the nucleus. He realized that atoms consisted of a tiny, dense nucleus surrounded by electrons. But what was the nucleus made of? In 1932, James Chadwick discovered the neutron. The nucleus consisted of protons and neutrons, but this raised a puzzle. Protons are positively charged. They repel each other. What held them together in the nucleus? There must be a new force, stronger than electromagnetism, that binds nucleons together. This became known as the strong nuclear force. Meanwhile, physicists were discovering other particles. The muon, discovered in 1936, was similar to the electron, but much heavier. The pion, discovered in 1947, was involved in nuclear forces. By the 1960s, physicists had discovered dozens of particles: protons, neutrons, electrons, muons, pions, kaons, and more. This proliferation of particles was puzzling. Were these fundamental particles? Or were they composed of something more fundamental? In 1964, Murray Gell-Mann and George Zweig independently proposed that all these particles were composed of more fundamental particles called quarks. There were three types of quarks: up, down, and strange. The proton consisted of two up quarks and one down quark. The neutron consisted of one up quark and two down quarks. The pion consisted of a quark-antiquark pair. This model explained the properties of the known particles remarkably well. But there was a problem. No one had ever observed a free quark. Quarks seemed to be permanently confined inside particles. This became known as color confinement, and it's one of the enduring mysteries of particle physics. As more particles were discovered, physicists realized there must be more quarks. In 1974, the charm quark was discovered. In 1977, the bottom quark. In 1995, the top quark. So there are 6 quarks, arranged in 3 generations. Each generation is heavier than the previous one. Similarly, there are leptons, the electron, muon, tau, and their associated neutrinos. All of these particles are described by the Standard Model. Now let me explain the Standard Model in more detail. The Standard Model is a quantum field theory. It describes nature in terms of fields permeating all of space. A quantum field is different from a classical field. A classical field has a value at every point in space. A quantum field has quantum fluctuations. It can never be exactly zero because of the uncertainty principle. When you excite a quantum field, you create particles. The excitations of the electron field are electrons. The excitations of the quark field are quarks. Different fields interact with each other according to specific rules. The strength of the interaction is determined by coupling constants. The Standard Model includes 17 fundamental particles, not counting the Higgs boson, which makes 18. There are 6 quarks, 6 leptons, 4 gauge bosons that mediate forces, and the Higgs boson. The 4 gauge bosons are the photon, which mediates electromagnetism, the W and Z bosons, which mediate the weak nuclear force, the gluon, which mediates the strong nuclear force. These bosons have different properties and behaviors, but they're all understood as excitations of underlying quantum fields. The strong nuclear force is described by a theory called quantum chromodynamics, QCD. Quarks interact by exchanging gluons. The weak nuclear force is described by the electroweak theory, which unifies electromagnetism and the weak force. The Standard Model doesn't include gravity. Gravity is described by Einstein's general relativity, which is fundamentally different from quantum field theory. Reconciling gravity with quantum mechanics is one of the greatest open problems in physics. And now let me discuss the properties of the standard model particles in more detail. Quarks come in 6 flavors: up, down, strange, charm, bottom, and top. The up and charm and top quarks have electric charge plus 2/3. The down strange and bottom quarks have electric charge minus 1/3. Quarks also have another property called color charge. There are 3 colors, red, green, and blue, and 3 corresponding anticolors. A quark always has a color. When quarks interact by exchanging gluons, the colors can change, but the total color is conserved. Quarks with color charge experience the strong force. This is why they're confined inside hadrons, particle containing quarks. A hadron must have 0 net color, so a quark-antiquark pair must have a quark of one color and an antiquark of the corresponding anticolor. Or 3 quarks must have red, green, and blue colors, or 3 anticolors. This is why we never observe free quarks. The strong force becomes stronger as quarks are pulled apart, making it impossible to separate them. Leptons are particles that don't experience the strong force. They only experience the electromagnetic and weak forces. The electron has charge -1. The electron neutrino has charge 0. The muon has charge -1, and the muon neutrino has charge 0. The tau has charge -1, and the tau neutrino has charge 0. These particles and their antiparticles are the fundamental building blocks of matter. Everything you see, your body, the air you breathe, the stars in the sky, is made of up quarks, down quarks, and electrons primarily. The mesons, taus, and strange, charm, and bottom quarks decay quickly and are only produced in high-energy collisions. Now, let me discuss force-carrying particles in more detail. The photon is the force-carrying particle of electromagnetism. It has 0 mass and travels at the speed of light. Photons are emitted when charged particles accelerate. They carry electromagnetic force between charged particles. The W and Z bosons mediate the weak nuclear force. They have mass. The W boson weighs about as much as a krypton atom. The Z boson is slightly heavier. The fact that they have mass means the weak force is short range. It only operates over distances smaller than the Compton wavelength of the W and Z bosons. When a W boson is emitted, the emitting particle changes type. A down quark can emit a W boson and become an up quark. This is how beta decay works. A neutron, down, down, up, emits a W boson and becomes a proton, up, down, up. The Z boson is different. It's neutral, so particles that emit it don't change type. A quark can emit a Z boson and remain a quark, though possibly with different direction and energy. The gluon is the force-carrying particle of the strong nuclear force. Like the photon, it's massless and travels at the speed of light. But unlike the photon, gluons interact with each other. This self-interaction makes the strong force fundamentally different from electromagnetism. It's this self-interaction that leads to asymptotic freedom, the property that the strong force becomes weaker at higher energies. This might seem counterintuitive, but it's a consequence of quantum mechanics. At very short distances, high energies, the strong force coupling constant is small. This is why the early universe, when temperatures were extremely high, behaved almost like a plasma of free quarks and gluons, even though quarks are confined in nucleons at the low temperatures we observe today. Now let me discuss the Higgs mechanism in more detail. The Higgs field is a quantum field that permeates all of space. Unlike other fields, the Higgs field has a non-zero value even at its lowest energy state. This is called the vacuum expectation value, or VEV. Particles interact with the Higgs field by a coupling called the Yukawa coupling. The strength of the coupling determines how strongly the particle interacts with the field. When a particle moves through space, it's constantly interacting with the Higgs field. This interaction resists the particle's motion, giving it an effective mass. Particles that couple strongly to the Higgs field are heavy. Particles that couple weakly are light. The photon doesn't couple to the Higgs field at all, so it remains massless. The W and Z bosons couple to the Higgs field. At low energies, they appear massive. But at very high energies, high temperatures, the Higgs field's VeV goes to zero. The W and Z bosons become massless, and the electromagnetic and weak forces merge into a single electroweak force. This happened in the early universe, fractions of a second after the Big Bang, when temperatures were above a few hundred giga-electronvolts. As the universe expanded and cooled, the Higgs field's VeV became non-zero. The W and Z bosons acquired mass. The electroweak force split into separate electromagnetic and weak forces. This process is called electroweak symmetry breaking. The discovery of the Higgs boson proved that this mechanism actually occurs. The Higgs boson is an excitation of the Higgs field. Now let me discuss the experimental techniques used to detect particles in detail. When particles are created in collisions at the LHC, most have extremely short lifetimes. They decay into lighter particles almost immediately. By reconstructing the decay products, physicists can infer the properties of the original particle. For example, the Higgs boson decays in several ways. One important decay channel is to two Z bosons, each of which decays to two leptons. So the Higgs decay signature is 4 leptons. By looking for events with 4 well-separated leptons of high energy, physicists can identify Higgs boson events. Similarly, the top quark is too heavy to exist in the real world. You can't find a top quark in a block of matter. It only exists for a fraction of a second when created in collisions. The top quark immediately decays to a W boson and a B quark. The W decays to either 2 quarks or a lepton and a neutrino. The B quark creates a jet of particles. By looking for this characteristic decay pattern, physicists can identify top quark events. The B quark is interesting because it has a long lifetime compared to other heavy quarks. A B quark can travel a few millimeters before decaying. This allows physicists to identify B quarks by looking for secondary vertices, points where particles seem to come from rather than from the primary collision point. Jets created by different types of quarks have slightly different properties. A gluon jet is broader than a quark jet. A B jet has a distinctive pattern from the long-lived B hadron. By identifying the types of jets, physicists can infer what particles were created in the collision. This jet identification is crucial for modern particle physics. Much of what we observe consists of jets, and correctly identifying them is essential for discovering new particles. The missing energy signature is also important. If a neutrino is created in a collision, it passes through the detector without interacting. Its energy isn't measured, but energy is conserved. So if the total energy of the outgoing particles is less than the incoming energy, the missing energy must have carried away by neutrinos or other undetected particles. Looking for large missing energy can indicate the production of undetectable particles, which might be dark matter or other exotic particles. Now let me discuss some specific results from CERN experiments in more detail. The discovery of the W and Z bosons in 1983 was monumental. It confirmed the predictions of the electroweak theory. The W boson had been predicted to have mass around 80 gigaelectronvolts. When discovered, it was found to have mass 80.3 gigaelectronvolts. The agreement between prediction and experiment was remarkable. Similarly, the Z boson was predicted to have mass around 91 gigaelectronvolts. The measured mass was 91.2 gigaelectronvolts. This triumph of theoretical prediction and experimental confirmation validated the electroweak theory and confirmed that physicists were on the right track in understanding fundamental forces. The precision measurements of the Z boson properties allowed physicists to test the Standard Model at unprecedented accuracy. By measuring how the Z boson couples to different types of quarks and leptons, physicists could test whether the Standard Model predictions were correct. The measurements were consistent with the standard model to incredible precision, better than 1 part in 1,000 in many cases. But crucially, the measurements also provided indirect information about the Higgs boson. Before the Higgs was directly observed, physicists could use precision measurements of other particles to infer the Higgs mass. The Higgs couples to virtual W and Z bosons. These virtual bosons affect the properties of the real W and Z bosons. By carefully analyzing the precision data, physicists predicted that the Higgs boson should have a mass between 115 and 135 giga-electron volts. When the Higgs was discovered in 2012 at 125 giga-electron volts, it fell right in the predicted range. This was a triumph of precision physics. Now let me discuss the future of CERN in more detail. The LHC currently operates at about 14 TeV center of mass energy. It will be upgraded to increase luminosity and collect more data, but higher energies will require new machines. The future circular collider would be 100 kilometers in circumference and could operate at energies up to 100 TeV. At 100 TeV, you could probe physics at much shorter distances and might discover new particles and forces. But such a machine would be enormously expensive, hundreds of billions of dollars. It would require international cooperation on a scale exceeding even the LHC. Is it worth it? Will higher energies reveal new physics? Physicists are uncertain. It's possible that new physics only appears at energies beyond reach. It's also possible that the standard model is more fundamental than we think. But the drive to explore continues. Understanding the deepest levels of reality has always been one of humanity's great quests. Now let me discuss dark matter and dark energy, which CERN's research touches on. Dark matter makes up 80% of the matter in the universe. It doesn't emit light, so we can only detect it through its gravitational effects. Physicists have proposed that dark matter might be composed of particles that interact only gravitationally and rarely interact with normal matter. CERN searches for such particles. Experiments look for interactions between dark matter particles and normal matter. If dark matter is produced at the LHC, it would show up as missing energy in the detector. Dark energy makes up 68% of the energy density of the universe. It's causing the expansion of the universe to accelerate. We have almost no idea what dark energy is. It might be a cosmological constant, a fundamental property of space-time. It might be a dynamic field like the Higgs. CERN's research doesn't directly search for dark energy. It's too diffuse to detect at the LHC. But insights from particle physics might help understand it. Now, let me discuss the relationship between CERN and cosmology. The conditions in the early universe were extraordinarily hot and dense. Particles that don't exist today were abundant. By studying what happens in high-energy collisions at CERN, physicists simulate in miniature the conditions of the early universe. Observations from cosmology, such as the density of helium and deuterium, which depends on how the Big Bang nucleosynthesis proceeded, constrain theories of particle physics. Conversely, new particles discovered at the LHC might have implications for cosmology. For instance, if supersymmetric particles exist, they could be dark matter candidates. Finding them at CERN would have profound implications for understanding the universe. This interplay between particle physics and cosmology is one of the most exciting aspects of modern physics. Now let me discuss some of the technical challenges in running the LHC. The LHC is one of the most complex machines ever built. It requires extraordinary precision in many areas. The superconducting magnets have to be cooled to 1.9 Kelvin using liquid helium. The cryogenic system is massive and requires constant monitoring. If a magnet warms up, it loses superconductivity and enormous currents are interrupted, potentially causing damage. The detectors have millions of sensors and channels that have to be carefully calibrated and monitored. The data from the detector flows at rates of terabytes per second. Managing and analyzing this data requires sophisticated computing systems and algorithms. The trigger system has to make split-second decisions about which events to record. A mistake in the trigger software could cause physicists to miss important events. Despite these challenges, the LHC has been remarkably successful. It has operated for over a decade and made discoveries that reshaped particle physics. Now, let me discuss the human side of CERN. Thousands of physicists work at CERN, but they're not all based there. Most have home institutions elsewhere. CERN serves as a hub where physicists come for periods of weeks, months, or years to work on experiments. The collaboration is truly international. Large experiments like ATLAS involve thousands of physicists from hundreds of institutions across dozens of countries. This international collaboration is both a strength and a challenge. It brings diverse perspectives and expertise. But coordinating thousands of people across time zones and cultures is complex. Yet somehow it works. Physicists are united by a shared goal: understanding nature. I've visited CERN, and there's a palpable sense of purpose. People are working on problems that matter. There's also a sense of camaraderie. Physicists working on different experiments collaborate and share ideas. The CERN cafeteria is famous as a place where physicists from different experiments run into each other and discuss physics. This casual exchange of ideas is valuable. Sometimes the insight that cracks a difficult problem comes from a conversation with someone from a different experiment. CERN is also a training ground for young scientists. Graduate students and postdocs work on the forefront of research. They learn not just the technical skills of particle physics, but also how to think critically, work collaboratively, and communicate complex ideas. Many of these young scientists go on to leadership positions in science and industry. Now let me discuss some of the philosophical questions raised by CERN's research. One question is about the nature of reality. Are quarks and electrons fundamental? Or are they made of something more fundamental? Physicists have looked for substructure in electrons and quarks and found none down to extremely small scales. It's possible that quarks and electrons are truly fundamental, not composed of anything smaller. But it's also possible that they're composite, and we just haven't achieved high enough energies to see their substructure. A higher energy accelerator might discover that quarks and electrons are made of even more fundamental particles. This journey toward fundamental constituents might never end. There might be an infinite sequence of layers, each made of more fundamental particles, stretching forever. Or there might be a bottom layer, truly fundamental particles that have no substructure. We don't know which is true, but CERN's research is helping us find out. Another philosophical question is about the completeness of physics. Will physics ever be complete? Some physicists hope for a theory of everything, a single framework that describes all particles and forces. Others argue that a complete description of all physical phenomena might be impossible in principle due to limitations in computational complexity or quantum effects. Still others think the question is ill-posed, that there might not be a meaningful sense in which physics is complete. These are deep philosophical questions. CERN's experimental results inform them, but they transcend physics. Now let me offer some final thoughts on CERN's significance and meaning. CERN represents the pinnacle of human scientific achievement. It's a complex machine built through international cooperation, designed to probe the deepest mysteries of nature. The fact that such a machine exists and operates successfully demonstrates humanity's capability to accomplish extraordinary things. The discoveries made at CERN, the Higgs boson, the precise measurements, the constraints on new physics, will influence physics for generations. Even if CERN never makes another discovery, it would be historically significant for what has already been accomplished. But CERN likely will make more discoveries. The HLLHC will collect more data. Perhaps rare decays will be observed. Perhaps hints of new particles will emerge. Or perhaps CERN will find nothing beyond the standard model, suggesting that either new physics is at much higher energies or that the standard model is more fundamental than we thought. Either way, CERN is advancing human knowledge. And that's ultimately why CERN exists, not for practical applications or economic benefit, but for the fundamental human drive to understand reality. This drive has existed since humans first looked at the stars and wondered what they are. CERN continues that ancient tradition, using 21st century technology to probe questions that philosophers have asked for thousands of years. In doing so, CERN reminds us that humans are capable of profound curiosity, creative problem solving, and meaningful collaboration. These are deeply human qualities, and CERN is a monument to them. Now let me discuss in detail specific discoveries that have shaped particle physics. The discovery of the muon in 1936 was surprising. The muon is similar to the electron, but about 207 times heavier. This raised a question. Why does the electron have such a light partner? Why does the muon exist at all? No one predicted the muon. It was an unexpected discovery that prompted new thinking about particle physics. The discovery of the muon led physicists to recognize that there might be multiple generations of matter. Later, the tau lepton was discovered, even heavier than the muon, and each lepton has an associated neutrino. So there are 3 generations of leptons: the electron and electron neutrino, the muon and muon neutrino, the tau and tau neutrino. Similarly, there are 3 generations of quarks. This threefold repetition is one of the great mysteries of particle physics. Why are there exactly 3 generations? Why not 1 or 5 or 100? The standard model doesn't explain this. It simply states that there are 3 generations. Finding an explanation for the number of generations might provide insight into physics beyond the standard model. Another major discovery involved CP violation in the B-Meson system. CP violation means that the laws of physics are not exactly the same when you reverse the direction of time and exchange particles with antiparticles. This was unexpected. For many years, physicists thought CP symmetry was exact. But in 1964, CP violation was discovered in the decay of kaons. Later, CP violation was discovered in B-meson decays. The asymmetry between how B-mesons and anti-B-mesons decay gives physicists a window into the fundamental asymmetry between matter and antimatter. Measurements of CP violation in B decays have precisely tested the standard model and found agreement. But the measured asymmetry is too small to explain why the universe is made of matter rather than antimatter. This suggests there's additional CP violation from physics beyond the standard model. CERN is actively searching for this new source of CP violation. Now let me discuss the tau lepton in more detail. The tau is the heaviest lepton, weighing about 1.78 gigaelectronvolts. It's about 3,500 times heavier than the electron. The tau is unstable. It decays almost immediately into lighter particles, usually a combination of pions and kaons and a neutrino. Because it's so short-lived, the tau is only observed in high-energy collisions. You can't find taus in ordinary matter, but studying how taus decay gives information about the weak force and the properties of fundamental particles. Taus are rarely produced at the LHC because their production cross-section, the probability of producing them, is small. But when they are produced, they're distinctive signatures that can help identify interesting events. Now let me discuss neutrinos in more detail. Neutrinos are elusive particles. They barely interact with matter. A neutrino can pass through the entire Earth without hitting a single atom. This makes them extremely difficult to detect. You need enormous detectors with sensitive sensors to observe the rare collisions between neutrinos and matter. But neutrinos are incredibly abundant. Trillions of them pass through your body every second from the sun and from cosmic rays. Neutrinos come in three types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. One of the great discoveries of late 20th century physics was that neutrinos have mass. For decades, physicists thought neutrinos were massless. But experiments showed that neutrinos can oscillate, transform from one flavor to another as they travel. This oscillation is only possible if neutrinos have mass, though the mass is extremely small, less than 1/1,000,000th the mass of an electron. The discovery of neutrino mass showed that the standard model is incomplete. The standard model assumed neutrinos are massless. How neutrinos acquire mass is an open question. It might involve physics beyond the standard model. CERN's experiments on neutrino physics, though not directly probing neutrinos, contribute to our understanding of the weak force, which governs neutrino behavior. Now let me discuss precision measurements and their importance. Many of CERN's discoveries have come not from observing new particles, but from precise measurements of known particles. For example, the mass of the W boson has been measured to high precision at CERN and other accelerators. These precise measurements test the predictions of the standard model. If measurements deviate from predictions, it might indicate new physics. Over the past decades, physicists have compiled hundreds of precise measurements from multiple experiments. Most agree with the standard model, but a few show small tensions, discrepancies that might indicate new physics. These tensions are small individually, but together they paint a picture of something we don't yet understand. This is how modern particle physics discovery works: small deviations that accumulate evidence for new physics. It's less dramatic than discovering a new particle, but it's how most progress actually happens. Now let me discuss the role of supersymmetry in current research. Supersymmetry is a hypothetical symmetry that relates bosons, force-carrying particles, to fermions, matter particles. In supersymmetric theories, every boson has a fermionic superpartner, and every fermion has a bosonic superpartner. The electron would have a supersymmetric partner called a selectron. The photon would have a partner called the photino. These supersymmetric particles would be heavier than their standard model partners and wouldn't exist at low energies. Supersymmetry is appealing for several reasons. It elegantly unifies bosons and fermions. It provides a dark matter candidate, the lightest supersymmetric particle, or LSP. It helps solve the hierarchy problem. Why gravity is so weak compared to other forces? CERN has searched extensively for supersymmetric particles but hasn't found any yet. If supersymmetry exists, the superpartners must be heavier than previously thought, beyond the LHC's reach. Alternatively, supersymmetry might not exist, and physicists need to find another way to solve the hierarchy problem. Now let me discuss the hierarchy problem in detail. The hierarchy problem asks, why is gravity so much weaker than the other forces? The ratio of the gravitational force to the electromagnetic force is about 10 to the power of minus 40. It's an enormous disparity. Why such a big difference? Is there a deeper reason? Or is it just how the universe happens to be? Various solutions to the hierarchy problem have been proposed. Supersymmetry would protect the weak scale from being pulled toward the Planck scale, where gravity becomes strong. Extra dimensions could explain why gravity appears weak. Gravitons leak into extra dimensions, making gravity weaker in ordinary space. The universe could be part of a multiverse, with different strengths of gravity in different universes. Anthropic reasoning. Technicolor or other composite models might explain the hierarchy without requiring new particles at the TeV scale. CERN's experiments test these hypotheses by searching for signatures of extra dimensions or new strong interactions. Now let me discuss how physicists think about new physics. When physicists search for new particles or forces, they don't search blindly. They have theoretical predictions about what might exist. These predictions come from several sources: theories that extend the standard model, supersymmetry, technicolor, extra dimensions, etc. Empirical hints from precision measurements that deviate from standard model predictions, philosophical considerations about what laws of physics should look like, symmetries, naturalness, elegance, observational puzzles from cosmology, dark matter, dark energy, matter-antimatter asymmetry. Physicists use these predictions to guide their experimental searches. They design detectors to be sensitive to the specific signatures predicted by the theory. This is more efficient than searching for every conceivable new particle, but it also means that if new physics takes an unexpected form, something theorists didn't predict, it might be missed. This is a limitation of modern physics. Our search strategies depend on our theoretical prejudices. Now let me discuss some of the technical innovations that have come from CERN research. One major innovation is superconducting magnet technology. CERN developed and refined the superconducting magnets used in the LHC. These magnets are now used in medical devices, MRI machines, other research facilities, and industrial applications. Another innovation is silicon detector technology. The detectors at the LHC use silicon microstrips and pixels to track charged particles. This detector technology has been refined and improved. It's now used in medical imaging, industrial inspection, and other applications. CERN pioneered large-scale data analysis techniques that have become standard in other fields. Methods for handling petabyte-scale datasets, for managing distributed computing systems, for validating results through statistical testing. These techniques developed at CERN are now used in data science generally. The World Wide Web itself was invented at CERN to solve a research problem. So while CERN's primary mission is scientific discovery, it has generated many technological innovations with broader impact. Now let me discuss the public understanding of particle physics. Particle physics is often seen as abstract and removed from everyday life. People might wonder, why does it matter if there's a Higgs boson? How does finding the top quark affect my life? These are fair questions. Fundamental research doesn't have immediate practical applications. But historically, fundamental research often leads to practical applications years or decades later. Maxwell's equations describing electromagnetism were pure theory. A century later, they enabled radio, television, and wireless communication. Quantum mechanics was abstract pure science. It led to semiconductors, lasers, and nuclear energy. Who knows what applications might come from understanding the Higgs or searching for dark matter. But beyond practical applications, there's the value of knowledge itself. Humans are curious creatures. We want to understand the universe. This drive to understand is one of humanity's noblest instincts. CERN represents humanity taking this drive seriously, dedicating resources to understanding nature at its deepest level. Now, let me discuss CERN's role in educating the public about science. CERN maintains an excellent website with information about particle physics and the LHC. The facility offers public tours where people can learn about the experiments and the physics. CERN publishes outreach materials and videos explaining the research. Scientists at CERN give public lectures and participate in science festivals. This public engagement is important. It demystifies science and helps people understand what physicists are doing. It also builds public support for fundamental research. When people understand what CERN is trying to accomplish, they're more likely to support the funding. Now let me discuss the next generation of experiments and facilities. The HLLHC will increase data by a factor of 10, potentially revealing rare processes. Beyond that, larger accelerators are being proposed. The International Linear Collider would collide electrons and positrons at high energies, complementing the LHC's proton-proton collisions. The Future Circular Collider would operate at even higher energies. Different types of colliders have different advantages. Electron-positron collisions are cleaner, no confusing debris from quark interactions, but have lower available energy. Proton-proton collisions have more energy but messier debris. Each type of collider probes different physics and provides complementary information. Now let me discuss the role of theory in guiding experiments. Theory and experiment work together in particle physics. Theorists predict what experiments should look for. Experimentalists test these predictions. If experiments confirm predictions, it validates the theory. If experiments contradict predictions, it reveals new physics. But sometimes experiments find things theorists didn't predict. In these cases, theorists have to revise their understanding. This interplay between theory and experiment has been the engine of progress in particle physics. Some of the greatest physicists have moved between theory and experiment, using insights from one to inform the other. Now let me discuss the challenge of explaining particle physics to non-specialists. Particle physics involves abstract concepts that don't have easy everyday analogies. What is a quark? It's not like anything in everyday experience. What is the Higgs field? How can an abstract quantum field give particles mass? These concepts are genuinely difficult to convey to people without extensive physics training. Yet it's important to communicate. Taxpayers are funding CERN through their governments. They deserve to understand what they're funding. Scientists have to find creative ways to explain complex concepts. Analogies, metaphors, visualizations, and narratives can help. But there's always a trade-off between accuracy and comprehensibility. A perfect analogy doesn't exist. All analogies break down at some point. Scientists have to make judgment calls about what's important to communicate accurately and what can be simplified. Now let me discuss some of the unsolved problems in particle physics that CERN might help solve. The proton radius puzzle. The proton's radius measured using electrons differs from the radius measured using muons. This discrepancy might indicate new physics. The muon G2 anomaly. The muon's magnetic moment has a small measured value that differs from theoretical predictions. This might indicate new particles or forces. The flavor problem. Why are there 3 generations of quarks and leptons? Why do different generations have such different masses? The strong CP problem. Why doesn't the strong nuclear force violate CP symmetry when quantum chromodynamics predicts it should? The matter-antimatter asymmetry. Why is the universe made of matter rather than antimatter? These puzzles drive current research at CERN and might lead to discoveries of new physics. Let me discuss the specific structure of CERN and how it operates. CERN is managed by a director general who oversees the scientific program, technical operations, and administrative functions. The organization is divided into several departments. The accelerator and technology sector, which manages the LHC and accelerator systems. The physics sector, which oversees the detector experiments. The computing sector, which handles the enormous data processing and administrative functions. CERN has member states that contribute funding and resources. The organization operates on a consensus basis. Decisions are made with input from all member states. This governance model reflects the collaborative nature of CERN. It's not a top-down hierarchical organization, but a federation of member states working together for a common goal. The international nature of CERN is reflected in the composition of its staff. Physicists, engineers, and administrators come from dozens of countries. English is the working language, though you hear many other languages in the hallways. This international environment is one of CERN's greatest strengths. Different perspectives and approaches lead to better science, but it also creates logistical and cultural challenges. Coordinating activities across time zones and cultures requires careful management. The experiments at CERN are structured as collaborations. The Atlas collaboration includes over 3,000 physicists from 180 institutions in 40 countries. Running such a large collaboration is complex. There are committees, working groups, and formal processes for making decisions. But remarkably, these collaborations function well and make important discoveries. The collaboration structure allows physicists with limited resources to participate in state-of-the-art research. A graduate student from a small university can work on the Atlas experiment and contribute to world-leading physics. This democratization of access to advanced research is one of CERN's important social contributions. Now let me discuss the timeline for potential discoveries at the LHC. The Higgs boson discovery took decades of development, from theoretical prediction in the 1960s to experimental discovery in 2012. This long timeline isn't unusual. Major discoveries in particle physics often take many years from conception to realization. The discovery of the W and Z bosons also took decades. They were predicted in the late 1960s and discovered in 1983. Looking forward, physicists expect major discoveries from the HLL-HC era, starting in the late 2020s. With 10 times more data, physicists might observe rare decays predicted by the standard model but not yet observed, find deviations from standard model predictions indicating new physics, make precise measurements of Higgs properties that might reveal new physics, discover new particles or forces, but it's also possible that no new particles will be discovered. The LHC might accumulate data showing nothing beyond the standard model. If that happens, it would suggest either that new physics is at much higher energies or that the standard model is more fundamental than expected. Either way, the scientific value lies in understanding what nature is. Now let me discuss the role of computing in particle physics. Modern particle physics is impossible without high-performance computing. The LHC produces about 40 million collisions per second. Each collision produces data from millions of detector channels. This is about a petabyte of data per second. more data than is stored in the entire Library of Congress. The trigger system immediately reduces this to about 1,000 events per second. Even this reduced data stream produces about 100 terabytes per day. CERN sends this data to computing centers around the world. Physicists analyze the data using sophisticated algorithms and statistical methods. These computing challenges have driven innovation. Techniques developed to handle LHC data are now used in other fields like astronomy, genomics, and data science. The computing infrastructure at CERN consists of thousands of computers linked by high-speed networks. The worldwide grid, a distributed computing system, allows physicists to access computing resources at institutions worldwide. This is a remarkable example of international collaboration in computing. Now let me discuss some of the serendipitous discoveries that have come from physics research. The cosmic microwave background was discovered accidentally by Penzias and Wilson in 1964 when they were working on satellite communication antennas. They detected radiation noise they couldn't explain. Eventually, they realized they were detecting the leftover radiation from the Big Bang. This accidental discovery earned them a Nobel Prize and provided the best evidence for the Big Bang theory. Similarly, many discoveries in particle physics have come from looking for something else. Physicists might be searching for one type of particle and discover something unexpected. This is why exploratory physics research is valuable. You never know what you might find. CERN maintains openness to unexpected results. The detectors are designed to capture data about all particles produced in collisions, not just those physicists expect. This allows serendipitous discoveries when nature surprises us. Now let me discuss the sociological aspects of particle physics communities. Particle physics has its own culture and norms. There's an emphasis on rigorous analysis and peer review. Claims are scrutinized carefully before being accepted. There's also a collaborative spirit. Physicists from competing experiments share data and discuss results. This contrasts with some other fields where researchers keep results secret until publication. The particle physics community values elegance and mathematical beauty. Physicists believe that deep physical principles should be reflected in mathematical simplicity. This aesthetic sense has often guided theory development. There's also a tradition of skepticism toward revolutionary claims. Extraordinary claims require extraordinary evidence. This scientific conservatism protects against false discoveries. Now let me discuss the relationship between experiment and theory in more depth. A complete understanding of nature requires both. Theory provides the framework for understanding data. It predicts what should happen in different situations. Experiment tests these predictions and provides new data for theory to explain. When theory and experiment agree, it builds confidence in the theory. When they disagree, it indicates something deeper awaits discovery. The greatest physicists have been those who moved fluidly between theory and experiment. They used experimental insights to guide theoretical development and vice versa. In modern particle physics, this movement between theory and experiment is less common. Theorists and experimentalists often specialize in one or the other, but there's still valuable interaction. Theorists spend time at CERN discussing with experimentalists. Experimentalists attend theoretical conferences. This interaction keeps both communities connected. Now let me discuss some of the aesthetic and philosophical aspects of particle physics. Physicists often describe equations as beautiful or elegant. What makes an equation beautiful? Typically, it involves simplicity, symmetry, and universality.
An equation that describes many phenomena using simple symmetric principles is considered beautiful. Einstein's equation E equals mc squared is beautiful because it's so simple yet so profound. The standard model equations have a beauty. They describe all known particles and forces in a unified mathematical framework. But physicists suspect there's deeper beauty yet to be discovered. The ultimate theory of everything is imagined to be even more elegant and unified. This aesthetic sense motivates theoretical research. Now let me discuss CERN's role in fostering scientific careers. Thousands of physicists have launched their careers at CERN. Young scientists get exposed to cutting-edge research and the highest standards of scientific rigor. They develop expertise in specialized areas and make connections with leaders in the field. These experiences shape their careers. Many scientists who spent time at CERN return to their home countries and establish research programs influenced by what they learned. In this way, CERN's influence extends far beyond the laboratory in Switzerland. The organization plays an important role in developing scientific talent globally. Now let me discuss the media coverage of CERN. CERN often makes headlines when major discoveries are announced. The Higgs boson discovery in 2012 received enormous media attention. It was featured in newspapers worldwide. Science communicators work to explain the significance to general audiences. Media coverage can be double-edged. It raises public awareness and support for science, but it can also lead to misunderstandings or overstatements. Sometimes the media portrays physics as ready to solve everything, as though understanding the Higgs will solve global warming or cures diseases. Scientists have to carefully communicate what physics can and cannot do. Physics addresses fundamental questions about nature's laws. These are important and intellectually profound, but they have different timescales and applications than practical technology. Despite these communication challenges, media coverage
Generally plays a positive role by raising public interest in science. Now let me discuss the future of experimental physics beyond the LHC. The LHC is the most powerful accelerator today, but physicists have proposed larger and more powerful machines. The International Linear Collider would be a 30-kilometer straight tunnel for colliding electrons and positrons. The future circular collider would be a 100-kilometer circular tunnel where protons could be collided at energies up to 100 TeV. There are also proposals for even more exotic accelerators using novel approaches. Muon colliders would have some advantages over electron or proton colliders, but are technically more challenging. Plasma accelerators could produce high electric fields over short distances, potentially enabling compact high-energy accelerators. These future machines represent the next frontier in experimental physics. But they're enormously expensive and would require international cooperation on an unprecedented scale. Whether they'll be built depends on physics discoveries. Is there new physics waiting at higher energies? And political decisions. Will countries commit the resources? Let me discuss some of the key figures in the history of CERN and particle physics. CERN was founded on the belief that European nations could accomplish more together than separately. The founders envisioned an organization dedicated to peaceful scientific research in the aftermath of World War II. This was profoundly idealistic. Nations that had been enemies were deciding to cooperate on science. Early leaders like Edoardo Amaldi understood that science could transcend political divisions. The organization's reputation has been built by generations of scientists who have made discoveries and advanced knowledge. Physicists like Carlo Rubbia, who led the discovery of the W and Z bosons, demonstrated the power of the LHC concept. Theorists like Peter Higgs predicted the Higgs boson decades before its discovery. Experimentalists like Fabiola Gianotti and Lynn Evans led the teams that built the detectors and made the Higgs discovery. These individuals and thousands of others have shaped CERN into what it is today. Now, let me discuss the specific properties of some fundamental particles in more detail. The electron is one of the most stable particles known. Experiments suggest the electron lifetime is at least 10 to the 34th power years, far longer than the age of the universe. The electron's mass is about 0.511 mega electron volts per c squared. Its charge is exactly opposite to that of the proton. The electron's magnetic moment has been measured to incredible precision. These measurements test quantum electrodynamics, the theory of electrons and photons. The precision is so high, better than 1 part in a trillion, that the measurements can detect tiny contributions from other particles. The proton is composed of 2 up quarks and 1 down quark held together by the strong force. But the quarks only make up about 1% of the proton's mass. The rest comes from the energy binding the quarks together through gluon interactions. This is a profound insight. Most of matter's mass comes from force, not from particles themselves. The proton is remarkably stable. Experiments searching for proton decay have found no evidence that protons decay, suggesting the proton lifetime exceeds 10 to the 34th power years. The neutron is free only when inside a nucleus or in specific conditions. Outside a nucleus, a neutron decays into a proton, electron, and antineutrino, with a lifetime of about 880 seconds. This beta decay is mediated by the W boson and is crucial for nucleosynthesis in the early universe. Now let me discuss the relationship between CERN and other major physics projects. While CERN focuses on high-energy physics, other projects probe different aspects of nature. Gravitational wave observatories like LIGO detect ripples in space-time from colliding black holes. Telescopes like Hubble and the James Webb Space Telescope observe the distant universe. Neutrino detectors like IceCube observe neutrinos from cosmic events. X-ray observatories study high-energy phenomena in space. These different experiments probe complementary aspects of nature. A complete understanding requires insights from all of them. Now let me discuss careers in particle physics. A career in particle physics typically starts with an undergraduate degree in physics, followed by graduate school where you specialize in the field. After graduate school, most physicists do postdoctoral research before moving into permanent positions. Jobs in particle physics are found at universities, national laboratories, and research institutions. The job market is competitive. There are many physicists and relatively few positions, but those who enter the field find it rewarding. The intellectual challenges are profound. You get to work on fundamental questions about nature. You collaborate with brilliant colleagues from around the world. You contribute to humanity's understanding of the universe. These rewards compensate for the challenges and competitions of an academic career. Now let me discuss some of the ethical considerations in particle physics. Most physics research is peaceful scientific inquiry. But historically, the physics research has been connected to weapons development. The Manhattan Project, which developed nuclear weapons, was led by physicists. After World War II, many physicists became concerned about the implications of their work. They advocated for international agreements to limit nuclear weapons. Today, particle physics research is generally disconnected from weapons. CERN specifically does research in civilian science with no weapons applications, But physicists still grapple with ethical questions. How should scientific knowledge be used? Should some research be restricted? Who decides? These are important questions that extend beyond physics to society broadly. Now, let me discuss the role of luck and chance in scientific discovery. Many major scientific breakthroughs involved an element of chance. The Higgs boson discovery happened when the LHC was finally powerful enough to create them. The cosmic microwave background was discovered accidentally. Penicillin's discovery involved contamination in a bacterial culture that could have been discarded. But luck only helps when scientists are prepared to recognize it. Einstein didn't discover relativity by accident. He developed it through years of rigorous thinking. The Higgs boson wasn't discovered by chance. Theorists predicted it, and experimentalists searched systematically for it. So while luck plays a role, the foundation is rigorous, disciplined scientific work. Now let me discuss how CERN's work connects to other sciences. Particle physics is foundational science. Everything in the universe is ultimately made of particles described by quantum field theory. But particle physics doesn't directly address many questions that other sciences study. Biologists study life and organisms. But life's behavior depends on chemistry, which depends on electron configurations, which ultimately depend on quantum mechanics. Geologists study the Earth, but geological processes depend on nuclear decay rates and gravitational forces, both rooted in fundamental physics. Chemists study molecular reactions, but chemistry emerges from quantum mechanics applied to atoms and molecules. Astronomers study distant objects, but stellar evolution depends on nuclear physics processes inside stars. In this sense, particle physics is foundational to all other sciences. Understanding particles and forces provides the foundation for understanding everything else. But it doesn't mean particle physics is the most important science. Different sciences address different questions at different scales. The relationship is more like a foundation. Particle physics provides the basic principles, but each science has its own domain and questions. Now let me discuss how experimental results are validated and checked. When CERN announces a discovery, the result has typically been checked multiple times. An individual physicist or team analyzes data and finds a signal. They then check for possible errors. Could the signal be statistical fluctuation? Unlikely if the significance is very high. Could there be a systematic error in the detector or analysis? Multiple consistency checks needed. Could the background be underestimated? Detailed background studies required. After individual checking, the result goes to the collaboration for review. Other physicists who weren't involved in the original analysis examine the work independently. Only after passing these reviews does the result get presented publicly. Additionally, independent experiments can verify results. When ATLAS and CMS both detected the Higgs boson, it greatly increased confidence in the result. This system of checks provides confidence that announced discoveries are real, but it also means that small anomalies might not immediately be announced as discoveries. Scientists are conservative. Extraordinary claims require extraordinary evidence. Now let me discuss CERN's outreach and communication efforts. CERN takes seriously its responsibility to communicate with the public and scientific community. The organization maintains a website with extensive resources about particle physics and current research. CERN hosts public lectures where scientists discuss their work for general audiences. The facility offers tours where people can see the actual detectors and experimental equipment. CERN has created educational materials and videos explaining particle physics concepts. Scientists at CERN engage with media to explain research findings. This public engagement serves multiple purposes. It fulfills CERN's obligation to publicly funded research to explain results to taxpayers. It promotes science education and scientific literacy. It inspires young people to pursue careers in science. It builds public support for fundamental research. In an era of scientific skepticism and misinformation, CERN's clear communication is valuable. Now let me discuss the long-term vision for particle physics. Physicists dream of a complete unified theory describing all particles and forces. The ultimate vision is a theory that predicts all the fundamental parameters, the masses of particles, the strengths of forces, the number of generations. Such a theory would be profound. It would mean that the universe's structure is uniquely determined by logical necessity. Whether such a theory exists is unknown. Perhaps there's an infinite diversity of possible universes with different parameters, multiverse. Perhaps there are constraints we don't yet understand that uniquely fix the parameters. Research at CERN contributes to understanding these deep questions. Now let me discuss the role of approximations in physics. Physics makes progress through approximations and idealizations. We model particles as point objects, ignoring their internal structure. We treat space-time as smooth and continuous. We make approximations in our calculations. These approximations are useful because they simplify the problem while capturing the essential physics. But they're only approximations. The true theory might have different structure. As we probe deeper and make more precise measurements, we learn the limits of our approximations and develop more accurate theories. This iterative process, making approximations, testing them, refining them, is how physics progresses. Now let me provide a final summary of CERN's impact and significance. CERN has been one of the most successful scientific organizations in history. It has made discoveries that fundamentally changed our understanding of nature. It has developed technologies that have applications beyond physics. It has trained thousands of scientists. It has demonstrated that international cooperation can achieve remarkable things. It has inspired the public imagination about what science can accomplish. Looking forward, CERN will continue to probe nature's deepest mysteries. The LHC will collect more data. Upgrades will improve sensitivity. Perhaps new discoveries await. Perhaps surprises that challenge our understanding. Whatever the future holds, CERN represents humanity's best efforts to understand the universe. It's a monument to curiosity, to rigorous method, to international cooperation, and to the belief that understanding nature's laws is worth dedicating our resources to. In an uncertain world, CERN stands as a beacon of calm, rational inquiry into how nature works. That's a profound contribution. Let me discuss the timeline and future prospects for major discoveries. The Large Hadron Collider began operation in 2008. Its first major discovery, the Higgs boson, came in 2012. From 2015 to 2018, the LHC underwent long shutdown for maintenance and upgrades. It restarted in 2022 at higher energy than before. The LHC will continue running, collecting data and searching for new physics, until around 2030, when major upgrades will be implemented. The high luminosity LHC phase will begin around 2029 and continue through the 2030s, collecting 10 times more data than currently available. This increased data will enable better measurements of the Higgs boson, properties, search for rare Higgs decays that might indicate new physics, improved measurements of top quark properties, better limits on new particles and forces, discovery of rare processes predicted by extensions of the Standard Model beyond the HL-LHC era. Larger accelerators might be built in the 2040s or 2050s if new physics hasn't been discovered. The timeline for particle physics discovery is measured in decades, not years. This patience reflects the challenge of probing nature at the deepest levels. Now let me discuss some common misconceptions about particle physics. Misconception 1. Creating the Higgs boson produces a dangerous black hole. Reality. The Higgs boson decays almost instantly. It doesn't have time to form any dangerous object. And even if it did, the LHC couldn't create large black holes. The energies are too low. Misconception 2. Particle physics doesn't have practical applications. Reality. Many technologies developed at CERN have been applied in medicine, MRI machines, industry, and computing. Moreover, understanding fundamental physics has always eventually led to applications. Misconception 3. Physicists know what 95% of the universe is made of, but can't explain it. Dark matter and dark energy. Reality. Dark matter and dark energy remain mysterious, but they're a small part of what physicists study. We have good understanding of ordinary matter and forces. Misconception 4. CERN is trying to recreate the Big Bang. Reality. CERN creates conditions similar to fractions of a second after the Big Bang in tiny volumes. This is useful for studying early universe physics, but it's not recreating the entire Big Bang. Misconception 5. The LHC might destroy the world. Reality. Extensive safety analysis has shown the LHC is safe. Particle collisions happen naturally in Earth's atmosphere at far higher energies. These have been occurring for billions of years without incident. Addressing misconceptions is important for maintaining public trust in science. Now let me discuss the role of international cooperation in science more generally. CERN exemplifies what's possible when nations cooperate on science, but international cooperation faces challenges. Political tensions between nations, disagreements about research priorities, competition for funding, visa and immigration restrictions affecting scientists, geopolitical conflicts affecting collaboration. The Ukraine crisis in 2022 disrupted some CERN collaborations. Russian scientists whose country sanctions became unable to fully participate. This is unfortunate, but reflects the reality that science operates within geopolitical contexts. Yet despite these challenges, CERN persists as a place of international cooperation. Scientists continue collaborating across borders because the scientific questions are important and shared. This is why CERN matters. It shows that science can transcend politics. It demonstrates that humans can cooperate for noble purposes. Now let me discuss how physics research informs our understanding of the cosmos. Particle physics discoveries constrain models of the early universe. For example, the number of neutrino types affects how the early universe evolved. The properties of the Higgs boson affect the stability of the universe. The matter-antimatter asymmetry observed in particle physics must be explained by any theory of the Big Bang. Conversely, observations of the universe inform particle physics. Dark matter observations suggest new particles beyond the Standard Model. Dark energy observations suggest new physics. Gravitational wave observations of black hole mergers test our understanding of gravity and massive objects. This interplay between particle physics and cosmology is one of the most exciting frontiers in modern science. Let me discuss some of the most profound questions that particle physics addresses. The question of why particles have mass has now been partially answered by the Higgs mechanism. but it raises deeper questions. Why does the Higgs field exist? Why does it have the value it has? The question of CP violation, why there's more matter than antimatter, remains unsolved. CERN experiments search for additional sources of CP violation that might explain this asymmetry. The question of generation, why there are 3 generations of quarks and leptons, remains mysterious. Are there deeper principles that determine this number? The question of quantum mechanics, why do particles behave probabilistically rather than deterministically at the quantum level, touches on fundamental philosophical issues. Is probability fundamental to nature, or is it just our ignorance of deeper deterministic laws? The question of what lies beyond the standard model, whether there's supersymmetry, extra dimensions, technicolor, or something else entirely, drives experimental searches. The question of whether physics is even capable of answering these questions, whether there are fundamental limits to what we can know, is worth pondering. Now let me discuss the role of symmetry in physics. Symmetries play a central role in modern physics. Einstein's theories of relativity are based on symmetries. The laws of physics are the same in all reference frames. Quantum field theory is built on gauge symmetries, mathematical symmetries that relate particles of different types. The Standard Model is based on gauge symmetries. The SU3 symmetry of the strong force, the SU2 symmetry of the weak force, the U1 symmetry of electromagnetism. When physicists search for physics beyond the Standard Model, they often look for new symmetries. Supersymmetry would relate bosons and fermions. Grand unified theories would unify the strong and electroweak forces. String theory would introduce additional symmetries at the Planck scale. The search for new symmetries is motivated by the success of symmetry in understanding nature. Nature seems to prefer symmetric laws. Finding deeper symmetries often leads to deeper understanding. Now let me discuss the role of mathematics in physics. Physics is ultimately expressed in mathematical language. The fundamental laws are mathematical equations, Maxwell's equations for electromagnetism, Einstein's equations for gravity, the Dirac equation for electrons, the Yang-Mills equations for gauge theories. Why is mathematics so effective at describing nature? This is a profound question. Some physicists argue that mathematics is fundamental to reality, that the universe is made of mathematics. Others argue that mathematics is just our best tool for describing nature, but nature might be fundamentally non-mathematical. CERN's discoveries provide data about how nature works. Physicists use mathematics to organize and interpret this data. The fact that mathematical theories so accurately predict experimental results suggests a deep connection between mathematics and nature. Now let me discuss the future of theoretical physics. Theoretical physics faces a challenge. The Standard Model works too well. It explains almost all experimental data at accessible energies. This success is wonderful for science, but it means there are fewer hints about what lies beyond. In the past, experimental anomalies guided theorists toward new theories. Today, anomalies are small and could be due to systematic errors rather than new physics. Some physicists worry that without clear experimental direction, theoretical physics might become increasingly abstract and divorced from empirical testing. Others are optimistic that new experimental hints will emerge from precision measurements and rare processes. The HLLHC might provide these hints. Or physicists might need a paradigm shift, a new way of thinking about fundamental physics. Now let me discuss the role of computational physics. Modern particle physics relies heavily on computers. Simulations predict collision outcomes based on theoretical models. Algorithms analyze detector data to extract physical information. Machine learning techniques identify rare event signatures in massive datasets. These computational tools have become essential for particle physics. Looking forward, quantum computers might revolutionize particle physics. Quantum computers could simulate quantum systems more efficiently than classical computers. This could accelerate discoveries in quantum mechanics and quantum field theory. CERN is investing in quantum computing research for future applications. Now let me discuss why CERN matters in 21st century context. In an era of climate change, artificial intelligence, and global challenges, one might ask, why fund basic particle physics? The answer involves several levels. Intellectually, particle physics addresses fundamental questions about reality that humans have asked for millennia. Practically, particle physics research has generated technologies with broader applications. Culturally, CERN demonstrates the value of international cooperation and rational problem solving. Inspirationally, CERN shows what humans can accomplish when we work toward understanding. Strategically, advanced physics research develops technologies and human capital that societies need. In a world fragmenting along many lines, CERN stands as an example of what unites us: curiosity about nature and commitment to understanding. This is valuable not just for science, but for human civilization. Now let me discuss what students interested in particle physics should know. If you're interested in particle physics, many paths are available. You could study physics and specialize in particle physics in graduate school. You could study engineering and work on detector construction or accelerator systems. You could study computer science and work on data analysis and computing systems. You could study mathematics and contribute to theoretical frameworks. Each path offers opportunities to contribute to frontier physics research. CERN and other laboratories actively recruit talented people from all backgrounds. If you're interested in fundamental physics, there's a place for you in this field. Now let me discuss how to stay informed about CERN's research. CERN maintains an excellent website with news, research updates, and educational resources. Scientific journals publish detailed papers on discoveries and measurements. Popular science books and documentaries explain particle physics for general audiences. Public lectures and online videos allow you to hear directly from physicists about current research. Social media and podcasts discuss recent discoveries and their implications. Staying informed is easier than ever. If you're curious about particle physics, there are many resources available. Now let me discuss what makes CERN special as a research institution. Many organizations do excellent physics research, but CERN is unique in several ways. It's built around the world's most powerful particle accelerator, attracting the best physicists globally. It operates as an international collaboration with member states supporting the mission. It has a culture of openness, sharing data and insights freely. It's dedicated purely to scientific understanding, with no military or commercial mission. It views itself as serving all humanity, not just member states. This combination of factors makes CERN unique and valuable. Let me discuss some specific measurements and recent results from CERN. The precise measurement of the Higgs boson mass showed it's about 125.1 giga-electron-volts. This mass is significant because it's close to the mass where theoretical predictions suggest something might change. If the Higgs mass were slightly different, the universe might be unstable. Physicists are studying whether this is coincidental or reflects a deeper principle. The measurement of the Higgs boson's decay modes provides information about how strongly it couples to different particles. So far, all measurements agree with standard model predictions. but precision measurements might reveal deviations indicating new physics. Another important measurement involves the top quark mass. The top quark mass has been measured to be about 173 giga-electron volts. The top quark is so heavy that it decays almost instantly. By studying its decay products, physicists measure its properties with high precision. The top quark mass enters into calculations of particle stability and theoretical predictions. Precise measurements of the top quark mass help test the standard model and constrain new physics. The W boson mass has also been measured with increasing precision. Recent measurements have revealed a small discrepancy between different experiments and predictions. This tension might indicate new physics, or it might resolve as better data arrives. Such small tensions are exactly what physicists watch for as hints of new physics. Now let me discuss rare decays and exotic processes. The LHC searches for rare decays predicted by the standard model but not yet observed. Examples include the decay of B mesons to invisible particles, or rare decays involving the Higgs boson. These rare processes are sensitive to new physics. If new particles exist, they could slightly change decay rates. By measuring these rare processes to high precision, physicists constrain theories of new physics. Now let me discuss the human experience of working at CERN. Scientists who have spent time at CERN often describe it as transformative. The combination of world-class research, international collaboration, and intellectual stimulation creates a unique environment. Young scientists learn from leaders in the field. They develop skills and perspectives that shape their careers. They make connections with colleagues from around the world. These relationships often last decades, influencing physics research globally. The experience of working at CERN is one that scientists treasure throughout their careers. Now let me discuss CERN's role in science education. Beyond research, CERN contributes to science education at multiple levels. CERN hosts summer school for physics students. The organization provides educational materials for high schools and universities. Scientists at CERN give talks and demonstrations in schools. CERN's website includes resources for students learning about particle physics. This educational mission helps inspire the next generation of scientists. It also helps improve science literacy generally. Now let me discuss the relationship between fundamental physics and applied physics. Fundamental physics asks questions about the nature of reality. Applied physics uses this fundamental knowledge to develop technologies. Often there's a long delay between discovery and application. Radio waves were discovered by Heinrich Hertz in 1887 through electromagnetic experiments. Decades later, Marconi developed radio communication technology. Semiconductors were discovered through quantum mechanics research. Decades later, transistors and integrated circuits revolutionized technology. Similarly, discoveries at CERN might lead to technological applications years or decades hence. This is why investment in fundamental research is valuable. It builds a foundation for future innovation. Now let me discuss how particle physics intersects with other fields. Particle physics connects with cosmology in understanding the early universe. It connects with condensed matter physics through shared mathematical frameworks. It connects with chemistry through quantum mechanics, understanding of electron behavior. It connects with geology through nuclear decay used for dating rocks. It connects with astronomy through understanding stellar processes powered by nuclear reactions. These connections show that particle physics is not isolated, but part of a broader scientific ecosystem. Now let me discuss the role of skepticism and criticism in science. Science advances through rigorous criticism and skepticism. When physicists propose new ideas, Others critically examine them. Experimental results are scrutinized for possible errors. Theoretical claims are tested against data. This culture of skepticism helps prevent false claims from being accepted. It also means that extraordinary claims face extraordinary scrutiny. This is why discoveries like the Higgs boson are so credible. They've passed rigorous testing. Now, let me provide a final thought on the significance of CERN and particle physics. Understanding the fundamental nature of reality is one of humanity's greatest endeavors. CERN represents humanity's commitment to this endeavor. Through CERN, we've learned that reality is stranger and more wonderful than classical physics suggested. Particles can be created from energy. Energy can be converted to mass. Particles can exist in superposition, in multiple states simultaneously. Particles can be entangled, affecting each other across distances. Forces can unify at high energies. The universe had a beginning in the Big Bang. These discoveries reshape how we understand existence. They challenge our intuitions about reality. They inspire wonder and awe. CERN is a testament to humanity's ability to discover truth through careful observation, logical reasoning, and creative thinking. It's a monument to curiosity, to the drive to understand, to the belief that reality can be comprehended through science. In this, CERN represents our highest aspirations. Now, let me offer a personal reflection on what CERN represents. CERN is a place where humans at our best, curious, cooperative, rigorous, imaginative, pursue understanding of nature. It's a place where a person's nationality doesn't matter, only the quality of their thinking. It's a place dedicated to knowledge for its own sake, not for military advantage or commercial profit. It's a place where young scientists can contribute to discoveries that reshaped human understanding. It's a place where the fundamental human drive to understand is honored and supported. In our turbulent world, CERN stands as beacon. It shows what humans can accomplish when we set aside our differences and work toward common goals. It shows that pure scientific research, seemingly disconnected from practical life, can advance knowledge in profound ways. It shows that international cooperation is possible, even when nations have tensions. It shows that curiosity about nature is a universal human value. These lessons extend far beyond physics. If we could apply CERN's model of cooperation and rational problem solving to broader global challenges, many problems could be solved. Climate change, poverty, disease, all could be addressed through the kind of dedicated, cooperative, evidence-based effort that CERN represents. CERN reminds us of humanity's highest potential. Let me provide more detail on the specific experimental techniques that make modern particle physics possible. When a proton-proton collision occurs at the LHC, the process unfolds in stages. First, the collision happens. Two protons collide head-on, each traveling at 99.9999% the speed of light. The collision releases enormous energy concentrated in a tiny volume, smaller than an atom's nucleus. This energy is converted into new particles through Einstein's E equals mc squared relation. Incredibly massive particles that don't normally exist are briefly created. These particles immediately decay into lighter particles. A cascade of decays occurs, producing a shower of particles flying outward from the collision point. The detectors must capture all this information within nanoseconds. The tracker records the paths of charged particles by detecting their ionization as they pass through silicon. The electromagnetic calorimeter absorbs electrons and photons, creating showers of particles. The hadronic calorimeter absorbs hadrons, particles containing quarks, measuring their energy. The muon chamber, the outermost layer, detects muons that penetrate the calorimeter. All of this data flows through the trigger system in real time. The trigger must decide within microseconds whether to record the event. It looks for signatures of interesting physics. High-energy leptons or jets suggest massive particles. Missing energy suggests invisible particles like neutrinos. Unusual patterns might indicate new physics. Only events passing the trigger get stored to disk. Later, physicists analyze the stored data in detail. They reconstruct what happened using computer algorithms. They look for patterns indicating the creation of specific particles. They calculate probabilities that various hypotheses explain the data. They perform statistical tests to determine significance. This entire process, from the initial collision to final results, can take months or years. Now let me discuss the challenge of extracting signal from background noise. Imagine you're looking for a rare particle that's produced once in every billion collisions. You have to look through billions of events to find it. Most events are background, particles that don't come from the physics you're searching for. To find your rare signal, you need to understand the background precisely. You develop ways to distinguish signal from background. The rare particle might have a distinctive mass, reconstructed from its decay products. The decay pattern might be unique. The rate of production might be different. By developing such distinguishing features, physicists can sift through enormous data sets. This requires deep understanding of both the physics you're searching for and the background processes. It requires developing new analysis techniques. It requires extensive validation that the method works. Only after all this preparation can a discovery be claimed with confidence. Now let me discuss the global LHC computing grid. The LHC produces data at petabyte scales. No single computing center could process all of it. So CERN created the worldwide LHC computing grid, a distributed computing system. It connects computing centers at universities and laboratories worldwide. These centers run standardized software for data analysis. Physicists submit jobs that run on whichever computers have capacity. This distributed approach harnesses enormous computing power. It also distributes the workload, so no single institution is overwhelmed. The computing grid enables particle physics collaboration at a scale previously impossible. Now let me discuss future technological improvements at the LHC. The LHC's magnets will be upgraded to allow higher beam currents, increasing luminosity. The detectors will be upgraded with faster electronics and more sensitive sensors. New computing systems will handle higher data rates. Improved trigger algorithms will use machine learning to identify interesting events. These upgrades will keep the LHC competitive for discoveries through the 2030s. After that, larger accelerators might be needed to continue pushing into higher energies. Now let me discuss CERN's role in training future leaders in science and technology. CERN provides opportunities for people at all career stages. High school students can participate in summer programs. Undergraduate students can do internships. Graduate students can do thesis research. Postdoctoral researchers can develop independent research programs. Early career scientists can lead research groups. Senior scientists can mentor and guide the field. This pipeline develops scientific leadership. People who have worked at CERN often go on to leadership positions in academia, industry, and national laboratories. They carry with them the values and approaches they learned at CERN. This influence extends CERN's impact far beyond the laboratory. Now, let me discuss the ethics of allocating limited resources to fundamental research. Some might ask, why spend billions on particle physics when there are pressing social needs? This is a legitimate question that deserves serious consideration. The answer involves several points. First, many countries can afford both to address social needs and to support research. It's not an either-or choice. Second, the amount spent on particle physics is actually small compared to other spending. It's about 0.0001% of global GDP in wealthy nations. Third, research has historically led to innovations that benefit society broadly. Fourth, pursuit of knowledge is a legitimate value. Humans care about understanding, not just material welfare. Fifth, the international collaboration at CERN promotes peace and cooperation. All these factors suggest fundamental research is worth supporting, but it's important to acknowledge the real trade-offs involved. Every dollar spent on research is a dollar that could theoretically go elsewhere. Society must decide what mix of spending best serves human flourishing. CERN represents one reasonable allocation, supporting the pursuit of knowledge about nature's laws. Now let me discuss the specific role of hadronization in particle physics. When quarks and gluons are produced in high-energy collisions, they cannot exist free in the real world. They're confined by the strong force. They rapidly hadronize, combine with other quarks to form hadrons. A single quark becomes a shower of hadrons, all moving roughly in the direction the original quark was moving. This jet of particles is what detectors actually observe. Understanding hadronization is crucial for interpreting experiments. Physicists use Monte Carlo simulations to model hadronization. These simulations generate many random collisions using QCD principles. By comparing simulated jets with real observed jets, physicists validate their understanding and refine simulation parameters. The accuracy of hadronization models affects the precision of physics measurements. Improving these models has been an important focus of CERN research. Now let me discuss the role of background processes in particle physics. When physicists search for rare signals, they must contend with background processes, more common collisions that can mimic the signal. Understanding and measuring the background precisely is essential for discovering rare events. Example, if physicists search for a rare decay producing 3 leptons, they must account for all other processes that can produce 3 leptons. Some backgrounds come from known processes that can be calculated theoretically. Others must be measured directly in control regions of the data. By developing sophisticated background estimation techniques, physicists can extract rare signals from noisy data. This requires deep understanding of both the signal and background physics. It requires developing clever analysis strategies that maximize signal efficiency while minimizing background contamination. The history of CERN is a history of developing increasingly sophisticated analysis techniques. Modern particle physics is as much about data analysis methods as about detector hardware. Let me provide additional detail on several important aspects of modern particle physics. The discovery of new exotic hadrons, particles made of quarks in unusual configurations, has been an active area of research. Historically, physicists expected hadrons to consist of either a quark-antiquark pair, mesons, or 3 quarks, baryons. But in the 2000s, new particles were discovered that don't fit these categories. Pentaquarks consisting of 4 quarks and an antiquark were discovered. Exotic tetraquarks consisting of 4 quarks have been observed. These discoveries challenge our understanding of how quarks can combine. They suggest the strong force produces a richer spectrum of bound states than previously thought. CERN and other experiments continue discovering new exotic hadrons, expanding our knowledge of QCD. Another active area is precision measurements of the Standard Model's electroweak theory. The strength of the electroweak coupling, the masses of the W and Z bosons, their decay properties, all are measured with increasing precision. These measurements can detect tiny effects from new physics. For example, if supersymmetric particles exist, they would contribute virtual loop diagrams that slightly modify measured quantities. Sensitive experiments looking for these small shifts provide indirect evidence of new physics. This is complementary to direct searches for new particles. Another important measurement involves the properties of the top quark. The top quark is the heaviest known particle, about 173 times heavier than a proton. Its large mass suggests it might have special significance, perhaps a connection to the Higgs or physics beyond the Standard Model. By measuring the top quark's properties, its mass, spin, decay modes, interactions with the Higgs, physicists gain insight into fundamental physics. The LHC produces millions of top quarks, allowing precise measurements. Another area involves searches for rare processes that the Standard Model predicts occur at very low rates. Examples include the decay of B mesons to muon pairs, or rare decays involving the Higgs boson. If new particles exist, they could change these rates. By measuring them precisely, physicists constrain new physics. The measurement of neutrino properties is another frontier. While CERN doesn't directly produce neutrinos in high-energy collisions like dedicated neutrino experiments do, CERN research contributes to understanding the weak force that governs neutrino behavior. Precise measurements of W and Z bosons constrain neutrino properties. The LHC's discovery of the Higgs provides insight into electroweak physics, which is intimately connected to neutrino physics. All of these measurements work together to paint a comprehensive picture of particle physics. No single measurement determines what physics exists beyond the Standard Model. But together they narrow down possibilities and guide theoretical development. This is the nature of modern particle physics. Not revolutionary breakthroughs every year, but steady progress through precision and comprehensive measurements. Let me offer one final perspective on what CERN represents for the future. CERN stands at a crossroads. The LHC has made incredible discoveries. The Higgs boson was found. Precision measurements test the Standard Model. But we're not done. Many mysteries remain. The next decade will be crucial. The HLLHC will collect more data. Perhaps it will reveal hints of new physics, small deviations from predictions that point towards something deeper. Or perhaps it will find nothing beyond the Standard Model, suggesting that new physics appears only at much higher energies. Either way, the search continues. CERN reminds us that the pursuit of knowledge is one of humanity's noblest endeavors. It reminds us that international cooperation can achieve remarkable things. It reminds us that curiosity and wonder are values worth celebrating. As we face challenges in the 21st century, climate change, resource scarcity, global health threats, we need the same dedication to rational problem solving that CERN exemplifies. We need the same commitment to facts and evidence. We need the same international cooperation. CERN shows these things are possible. In this, CERN is more than just a physics laboratory. It's a symbol of what humanity can achieve when we dedicate ourselves to understanding and cooperation. It's a place where curiosity is honored and supported. It's a reminder that knowledge itself has value. independent of immediate practical application. As long as humans wonder about the universe, about its origins, its structure, its laws, places like CERN will matter. They represent the best of human aspiration to understand. Thanks for watching. The interdisciplinary nature of modern particle physics cannot be overstated. A successful physicist at CERN needs knowledge of quantum mechanics, special relativity, statistical analysis, computing and programming, experimental design, and more. The field attracts brilliant minds from around the world who are fascinated by fundamental questions about reality. The collaborative environment at CERN brings together different perspectives and expertise. A physicist from Japan might work alongside engineers from France, computer scientists from the United States, and theorists from Brazil. This diversity of background and culture strengthens the research. Different perspectives lead to better problem solving. Different approaches lead to more comprehensive understanding. CERN's international nature is perhaps its greatest strength. Let me conclude by discussing what makes CERN unique among world laboratories. Many countries have physics laboratories. Many do important research. But CERN is unique in several ways. It's devoted purely to fundamental physics with no commercial or military applications. It operates as a truly international collaboration with member nations sharing governance. It has built the world's most powerful particle accelerator, designed specifically for discovering new particles. It attracts the world's best physicists who choose to work there despite competition from prestigious universities. It maintains a culture of openness, sharing data freely with the scientific community. It invests heavily in education and public engagement. It successfully balances ambitious long-term vision with pragmatic near-term achievements. These characteristics make CERN more than just a laboratory. It's a model for international scientific collaboration. Looking back at CERN's history, we see a pattern of ambitious goals followed by successful implementation. The organization sets targets and meets them, sometimes facing setbacks but ultimately achieving the vision. The LHC faced a serious accident in 2008 but was repaired and continued operation. Experiments faced technical challenges but overcame them through engineering innovation. Theoretical predictions proved correct when experiments tested them. This pattern of ambitious science followed by successful delivery builds confidence in CERN's future plans. Now let me discuss what finding new particles might mean for society. If CERN discovers supersymmetric particles, it would validate theories that have been developed over decades. It would open new avenues of research into fundamental physics. It might provide dark matter candidates, addressing a major cosmological mystery. If CERN discovers evidence for extra dimensions, it would revolutionize our understanding of space itself. If CERN finds hints of physics beyond current theoretical frameworks, it would indicate new directions for theoretical development. Any major discovery would be scientifically profound. It might have technological implications years or decades in the future. It would certainly inspire the next generation of scientists. The act of discovery itself, finding something completely new about nature, is inspiring. It renews our sense of wonder about the universe. It shows that mysteries remain to be solved. It demonstrates that human ingenuity and dedication can uncover nature's deepest secrets. This inspirational aspect of science shouldn't be overlooked. The pursuit of knowledge drives human progress. CERN represents this pursuit at its highest level. The future of particle physics is unwritten. Whether new discoveries await or the standard model stands supreme, the search itself is worthwhile. CERN embodies humanity's determination to understand reality. In this beautiful endeavor lies true meaning. CERN will continue probing nature's mysteries for decades to come. Scientists at CERN today are building the experiments that will make discoveries decades from now. Their work will shape human understanding for generations.